Hi, my name is Connor Herndon. I'm from the Society of Physics Students at the Georgia Institute of Technology. So this video is going to focus on just general practices, techniques, and notational tools that we use in physics generally. So it's going to be very basic, rudimentary, but hopefully this video will be able to give you some terms that you can look up later on your own time. So the first up is Einstein's summation convention. So this is a tool that's just generally used because whenever you have gigantic summations like it can be really hard to sum up everything, and these guys definitely get in the way of everything you wanted to write. So we have this fancy way of being able to write things without having to put the summation each time. The secret is you just don't put the summation each time. Instead of drawing the entire summation for everything you would ever want, you just say that this summation over all of I, all of j of aij, bij, you can just write that as aij, bij. You just drop the summation sign altogether. It's totally cool. That's what the convention is about. So it saves you a lot of space. And generally, if you ever see if you see an index that's repeated within an equation, you assume that it's summed over, unless it explicitly says that it's not. So the summation convention is useful for things like the dot product, where you will have two vectors put together. It's a special form of the inner product, where you put two vectors together and you get a scalar out. So this is, by definition, it's just the summation of ai, bi over all the indices. With the summation convention, you can just drop the summation, so you just have ai, bi. It's not too much, but it saves a lot of time usually, and also it's good just for you to recognize this in the future if you see this in a textbook. So the cross product is a bit like the dot product in that it's a product between two vectors, but instead of creating a scalar, the cross product creates another vector. It's useful for tons of things in physics if you haven't seen it already. The problem, though, is that it's got this really unique definition that doesn't really make too much sense when you look at it. It just looks like it's just insanity. So you've got this determinant here of the I, j, k in the directions, and the indices of each of the vectors. But you can actually reduce this with something. So there's this really useful tensor that comes up, and I absolutely refuse to look it up and figure out the actual pronunciation of this word, so you're going to have to deal with it if it's wrong. But I call it the Levi-Civita tensor. So it's this happy little guy, epsilon here, epsilon sub I, j, k, and it has unique properties in that it's positive 1 for an even permutation, I'll explain these later, negative 1 for an odd permutation, and then 0 otherwise. So an even permutation would be, if you picture I, j, k as being in a circle, increasing in alphabetical order, so I, j, k, that would be an even permutation. So would j, k, I, and k, I, j. If these indices are in that order, positively increasing about this circle, it's positive 1. If these indices go backwards, such as ikj, jik, or kji, it's minus 1. If any of these indices are repeated in any way, like if you had epsilon sub iij, the tensor would be 0. So you can think of epsilon as being a sort of cube of numbers, and each of these is an index, just like you would a matrix, but it's a cube, it's a tensor. So that was an extremely strange definition if you haven't seen it before, but the reason it's useful is that the cross product reduces it very nicely now. So then we would say that the ith component of the A cross B cross product would just be epsilon sub ijk, aj, bk. That's really wonderful because it looks really simple right here. It's a little bit confusing just to look at right now, but whenever you have multiple cross products together or cross products combined with dot products and things, just reducing things to an index notation makes things a lot prettier and a lot easier to manipulate. You're able to derive a lot more vector identities just by reducing it to something like this form. Now, if you've ever had to deal with matrix multiplication before, maybe you found it a little bit unintuitive, it doesn't make much sense. Yeah, well, it doesn't really. And you usually play this little finger game where you put your hands right here and you have to figure out what is going to be the answer based off of, what is this one multiplied by this one, then you move down the row in the column and things like that, and then you have to keep track of where these numbers go and everything. It's a little bit confusing. But luckily with the Einstein summation convention and other index trickiness, you can reduce this into something that makes a little bit more sense and it's a little bit cleaner. Simply put, this is a very basic definition of what you could consider matrix multiplication to be. It's the ikth component of the new matrix that is formed by the product of A and B is just equal to aij, bjk, where these are the indices multiplied together, and then you sum over all repeated indices. and the only repeated index in this situation would be j. So you sum over all of the j components, and you get the i kth component of this AB product.